All right, welcome back. So in this video, we'll be looking at the one of the great fundamental theorems in complex analysis, the Cauchy-Goursat theorem, right? Um, Named after two famous mathematicians. So here's the theorem. So suppose we have a complex function, f of z, that is analytic on a simply connected domain D, right? So you can so for any points for any points in your domain, we can draw a path, okay, that will connect those two said points in your domains. That's what's called simply connected. All right, so then for every closed contour C that's in D, um, the line integral of the closed curve C of f of z dz is equal to 0. Okay. The proof behind this is using another theorem in calculus called Green's theorem, named after George Green. Usually it's in Calc 3. So Green's theorem looks at a closed contour in 2 dimensions, and the line integral of a closed curve is equivalent to taking the double integral of the region that is inside that closed contour. R is what's called the region in that's encapsulated by C. Okay, so you don't have to write this down, but so the line integral of C, right, f of z dz, by definition, this is just f of z of t times z prime of t dt, right? So C, so this is equal to, so we'll have the line integral of the closed curve C of u of xy plus I of v of xy, and then we'll have a dx plus I times dy, right? And so this, in terms of the real and imaginary components, we'll have so u dx minus v dy, and then plus I times the line integral of the closed, that's not good, of the closed curve C of v dx plus u dy. Okay, plus u dy. So by Green's theorem, right? So this would be equal to the double integral of the region of, so in this case, we'll have minus the partial of v with respect to x minus the partial of u with respect to y dA plus I times the double integral of the region partial of u with respect to x minus the partial of v with respect to y dA. dA. So that's the imaginary component. Since f of z is analytic, we're going to use the Cauchy-Riemann equations, right? By the Cauchy-Riemann equations. By the Cauchy-Riemann equations. We have that this is equal to, well, partial of u with respect to y is equal to minus partial of v with respect to x. So the real component, so we'll have partial of v with respect to y minus the partial of v with respect to y, dA, plus I times, by the Cauchy-Riemann equations over here, partial of u with respect to x is equal to the partial of v with respect to y. So partial v with respect to x minus partial v with respect to x. Partial u with respect to x, I got that. So this equals to 0 plus 0i, which is 0. And that's what we wanted to prove. Okay. So, yeah, so this is a pretty powerful theorem. Okay. So, so let's go over an example on how we would use this. Yeah, so how we would use this. So the closed contour is the where the so the closed contour in this case is the circle of radius 1. Okay. So what we need to do is, so this here is f of z, right? So what we need to do is figure out where this function is analytic. Okay. Also, let's draw in the unit circle, right? So the unit circle would be this region, right? Right, so 0, 1, 1, 0, 0, minus 1, and minus 1, 0, right? So this is the closed contour they're talking about here, right? And f of z, the function that is in this line interval, z over 2z plus 3, is analytic, except where the denominator is 0. So in this case, it's minus 3 halves. So it's a point that's way out here, right? Minus 3 halves. Minus 3 halves plus 0i. So that is where the function is not analytic. So that's good. Okay. So the region, so R would be the region inside the unit circle. So this point is not inside the unit circle. So we're golden, right? So we have a closed contour, right? We can define a parameterization of that closed contour, right? And so by the Cauchy-Goursat theorem, okay, by the Cauchy-Goursat theorem, this line interval z divided by 2z plus 3dz is 0, okay? All right, it's that easy. Okay. And you can also verify this too, right? You can also verify this equals 0 by just doing the brute force, the parameterization, right? E to the IT. 0, t is in between 0 and 2 pi, right? 2 and pi. And so the line interval of z over 2z plus 3, right? So this equals to 0 to 2 pi dz. So this would be e to the so this will be e to the it divided by 2 times e to the it plus 3 times I times e to the it dt. Okay. We can do a u substitution. U equals e to the it, and then du is I times e to the it dt. So so in terms of u's, I'm going to leave out the limits in t here. So this would be u over 2u plus 3 du, okay? we can do another substitution. W equals 2u plus 3, which means that u is equal to w minus 3 over 2. And then dw is equal to 2 du, right? This is in u's. So in w's, this would equal to integral from 0 to 2 pi. That's in t. So we'll have w minus 3 over 2 divided by w times 1/2 du. Okay. So this equals to the integral from 0 to 2 pi of, so 1/2, I'll say. So this equals to 1/2 times the integral from 0 to 2 pi of w divided by 2w minus 3 over 2w dw. Okay. And so this equals to 1/2. 1/2 times, so that will be 1/2 w, which is 2u plus 3, but that would be 2 times e to the it plus 3. If we substitute everything back in, minus 3/2 times the natural log of the absolute value of 2 times e to the it plus 3. And this is where t is 0 and up to t equals 2 pi, right? Cosine of 2 pi is 1 and cosine of 0 is 1, right? So we'll have essentially 1/2 times 2 times 1 plus 3 minus 3/2 times ln of 2 plus 3. Okay. And then minus 2 times 1 plus 3 minus 3/2 times the natural log of the absolute value 2 plus 3. And that would be 0. Okay. So that's just one way to verify it. Okay. So this is a pretty powerful theorem. So because we can use this theorem for multiple connected domains. Okay. For multiple closed curves, I'll say. Okay. So if we have an example of a domain like this with a region that the function is not defined, let's say there, okay? And suppose we have some closed contour. Suppose we have some closed contour C. C right here, okay? Suppose we define the closed contour C here. Okay. So let me actually make this smaller. So yeah, so let me make this a little bit smaller. So suppose this white region here is where the hole is, okay? So so let's suppose we have a domain D that is not simply connected. It has a hole in it, right? So what we can do is so since there's a hole in this domain, our function, so suppose f of z is a function defined on D, okay? Then what we can do is we can draw in a closed contour right about that, where that region is, okay? And then we can go in the opposite direction of the contour C. So that means we're going to go this way. Okay. All right. Then what we can do next is we can draw in a bridge. A bridge. Let's say here. And in here. We'll call this AB. Okay. So the yellow curve I'll call C1. I'll call it C1. And the contour C is in blue. Okay. So what we can do is so by introducing the this line segment, the AB bridge, I'll say, we have created a simply connected domain, right? A simply connected so we have created a simply connected domain D, even though there was a hole that was defined by D, right? So we can somehow create a simply connected domain by traversing C counterclockwise, going through this bridge AB, and then traversing back along C1 clockwise, I'll say, right? So by the Cauchy-Goursat theorem, okay, the line integral of C plus the line integral of this line segment AB plus the integral of going in the opposite direction of the bridge AB of F minus, since we're going clockwise on C1, we have to put that a minus out front here. Minus the integral of C1 of F has to equal 0. So this means that the line integral of the closed curve C of F, this has to equal to the line integral of C1 of F dz. Okay. This last line right here, this is what's called the principle of deformation of contours. What this means is for any closed curve C, we can find another closed curve C1, which is easier to work with, right? So if we have a wacky closed curve C that is wrapped around some region where our function may not be defined, so like with this example here, well, we can figure out a way to deform this closed curve into another closed curve, which is easier to work with. And the Cauchy-Goursat theorem would be valid for this type of curve in our domain. Okay, so let's actually look at this property in action. So I'll show you with a example, right? Um, so there's the other example that I wrote out. Um, okay, so I'll just write it out. So compute the line integral of the closed curve C of 1 over z dz. Okay, here's one example. We want to compute the line integral of the closed curve C of 1 over z dz, where the curve is defined by the circle of radius 2, right? Now, if you notice, f of z equals 1 over z, this is an analytic function. Except at z equals 0. Okay. In order for this theorem, in order for the Cauchy-Goursat theorem to work, is valid in domains where f of z is analytic, right? So if we have the circle of radius 2, so here's our circle of radius 2, right? The circle of radius 2. The problem is our function is analytic on and inside the circle except at z equals 0. This point right here. Okay. So unfortunately, the Cauchy-Goursat theorem would not work. Okay. So what we need to do is we need to do the brute force work. Well, that's fine. Because we know the parameterization of the circle, right? The circle of radius 2. The parameterization, well, it's just 2 times e to the it, right? And then dz would be 2I times e to the it, right? The limits for t is in between 0 and 2 pi. So in terms of t, this equals to the integral from 0 to 2 pi of 1 divided by 2 times e to the it times 2I e to the it dt, right? E to the its will cancel, and also with the 2's. And so you'll have I times the integral from 0 to 2 pi of dt, which in this case is 2 pi I. So the integral of 1 over z dz equals to 2 pi I, right? I think we have seen this before in the previous video, right? So, so here's another example. I want you to work on this on your own, okay? Evaluate the line integral of the function 2z plus 1 divided by z squared plus z, where c is defined as the following curves. Part A is the circle of radius 1/2. Part B is the circle of radius 2. Part C, this is the circle, where was it? Z minus 3i equals 1. Okay, so let me zoom back out here. So what you need to do is evaluate this line integral of 2 times z plus 1 divided by z squared plus z, where the closed contour is defined as these closed contours. The modulus of z is 1/2, the modulus of z is 2, and then the modulus of z is z minus 3i is equal to 1. So try to work on these, and we'll see what you came up with as your answers. Okay. All right. So I assumed you worked on these examples, and let's actually go over it together. So what we want to do is we want to express this line integral 2z plus 1 divided by z squared plus z dz. Okay, so we're going to use Calc 2 techniques. So we're going to use partial fractions decomposition. So use partial fractions. Use partial fractions here. So 2z plus 1 divided by z times z plus 1. So right away, we can say that this function is analytic on the complex plane, except at z equals 0 and z equals -1, right? So take note of that. It's analytic at z equals 0 and then z equals -1, except at z equals 0 and z equals -1. So by using partial fractions, this equals to a over z plus b divided by z plus 1, right? Next, if we multiply both sides of this, if we multiply both sides of this equation by z times z plus 1, so we'll have 2z plus 1 equals to a times z plus 1 plus b times z. Okay, and this is plugging different values for z. So if z equals 0, we'll have that a is 1. Okay, so we'll have that a is 1. And if z equals -1, this would mean that -1 equals to minus b, which means that b is 1. Okay, which means that b is 1. So what that means is that this integral right here, this equals to the integral of the closed curve of 1 over z dz plus the line integral of c of 1 over z plus 1. Pretty sweet. Okay. So, okay. So we know that these functions are, so let me write out the functions over here. So dz plus c 1 over z plus 1 dz. Okay. So what that means is all we have to do is look at the pictures of our domains and see if they include z equals 0 or z equals -1, right? So 0 minus 1/2, and this is 1/2 0, and minus 1/2 0 there. Okay. So for part A, we know that the circle contains the origin, right? But it does not contain the point z equals -1. It's out here, right? It's outside of the circle. So it's analytic there, but it's not analytic at z equals 0. So what that means is, the integral of 1 over z dz would be 2 pi I, right? It would be 2 pi I. And this, by the Cauchy-Goursat theorem, this would be 0. So the line integral of this function along z, modulus of z equals 1/2, this would equal to 2 pi I. Okay. All right. Okay, so part B, this time, our circle would be the circle of radius 2. All right, so this is a circle of radius 2. Shoot. 2, 0, 0 minus 2, and then minus 2, 0. Okay. So what that means is these will include both values that are not analytic. So it includes z equals 0 and z equals -1. So these line integrals okay, so these line integrals we can draw in circles on each of these points and just use the parameterization, and we would get 2 pi I for the first quantity and 2 pi I for the second quantity. So this equals to 4 pi times I. Okay. And this is an important thing to mention. So let me write out a fact here to mention. So if f of z is analytic, along some closed contour C, except at z equals z0, the line integral of the closed curve C of dz divided by z minus z naught to the n. Okay, this integral would equal to either 2 pi I if n equals 1 and 0 if n does not equal 1. Okay. All right, so this refers to the deformation of closed curves, right? We can deform any closed curve into a circle, parameterize it, and we'll see if we'll have 0 if n does not equal 1, right? And if it equals to 1, if n equals to 1, we'll have 2 pi I. Okay, so that's an important thing to mention here. So for part B, we'll have 4 pi I here. And then for part C, we're looking at the circle of radius 1, but its center is at 0, 3. So it's 0, 3 here. So I have 0, 4, 0, 2, 1, 3, and minus 1, 3 here. Okay, so we're looking at the region. So the circle of radius 1 centered at 0, 3, the boundary and the region that's inside, right? the line integrals of these functions here, z plus 1. Okay. So c's here. Let me label out the c's, and then the c is there too. So, okay, so we know this function is not analytic at the origin and at z equals -1, right? Z equals -1. So these points are not in this region. So that means we can use the Cauchy-Goursat theorem, right? Cauchy-Goursat theorem. So this equals to 0, and this will also equal to 0. So that means the total line integral here would be 0. Okay? So that is basically what the Cauchy-Goursat theorem is all about. Okay? So I know that was pretty fast, but if you have questions, just let me know, and I'll guide you through the right direction. Okay, so here's some comprehension problems to work with. 2, 6, 8, 10, 14, 18, 20, 23, and 25. Okay, so for next time, we're going to be looking at the Cauchy integral formula and finishing off with integration in the complex plane. Okay, so thank you for watching, and I will see you all in the next video. Take care.